Hello everyone, and welcome back to a new episode of Advent of Code 2016. We're going to be looking today at my solution to day 24. As before on these episodes where I say we're talking about my solution, that's because I've already finished solving the problem and we're just going to look it over and discuss. So, day 24, air duct spelunking. You finally met your match. The doors that provide access to the roof are locked tight, and all of the controls and related electronics are inaccessible. You simply can't reach them. The robot that cleans the air ducts, however, can. It's not a very fast little robot, but you reconfigure it to be able to interface with some of the exposed wires that have been routed through the HVAC system. If you can direct it to each of those locations, you should be able to bypass the security controls. You extract the duct layout for this area from some blueprints you acquired, and create a map with the relevant locations marked, your puzzle input. 0 is your current location from which the cleaning robot embarks. The other numbers are, in no particular order, the locations the robot needs to visit at least once each. Walls are marked as hash signs, and open passages are marked as a period, as before in many of these puzzles. Numbers behave like open passages, although, of course, they also have the effect that there's a number there and you have to pick it up. So, for example, here's a map. So if you started at 0, the best way to collect all of these in any order is to head down to the 4, back up and around to the 1, and then over to the 2 and 3. So this is another graph search problem. We're trying to find the shortest path that fulfills all of the requirements. And so when I looked, well, let's pop over into Emacs, shall we? When I looked at my puzzle input, I was like, this is a pretty big map. Maybe this will finally be the one where red first search is no good and you need like at least a slightly directed A star search. It's not really. Oh, I just realized my terminal window is a lot larger than it usually is today, huh? Let's shrink that. How we doing? Make it smaller still. That should do. Okay. No, I thought I cleared the window. Whatever. Okay, so anyway, I looked at my puzzle input, and I was hoping, hey, maybe we need a directed search this time. And we don't really, which is too bad. But on the other hand, even a directed A star search is not a very good way to solve this problem. I didn't realize that, so that's what I did. I just grabbed my search thing from before, and I made it. Did I change this at all? No, I left search exactly the same as it was before. So we built a node class, which is like the plugin to our search, basically. We'll get to that in a minute. Let's just do some simple parsing first. I actually had not such an easy time figuring out the right way to parse this one. I was thinking like we want a node class, which has a pointer to the maze that it's a part of, and like how exactly do you model the pickups? That's what I chose to call the numbers 1 through whatever is the things that you have to pick up, and they're pickups, right? How do you model them? Do you keep track of like the ones that you have or the ones that you don't have? And what else did we need? Right, our position. So we need, and I don't know. And I was thinking of like parsing everything into a maze object and then iterate it and having the maze object like also return some information about where the pickups were or something. But eventually I realized that is kind of silly. To parse a seek of lines, still talking like Clojure. To parse an iterator of lines, we just convert it into a list, and we say that the resulting list of strings, that's our maze. We don't need any more about it than that. I was thinking of, I'll parse it into like an array of objects where there's a wall object and a floor object. It was like, no, that's maybe like a good way to model the problem, but unnecessarily complicated for what we need to do. We'll just leave it as a list of strings. And I decided that to save the pickups just as the ones remaining to be gotten, rather than like save where they all are and which ones you currently have. I'll just save the ones you have. So getting the XY coordinates attached to each character was, I don't know, once I thought about how to do it, not hard, but we have to keep notice whenever we're parsing a pickup and then save that coordinate here, and it's like, oh, okay, well, we'll just enumerate the lines. I guess so. Part of the trick is that the reason I had some trouble coming up with this really obvious and easy solution is that I was trying to do it all in one pass, which is what I would do in Clojure, because I have vectors that you can append to cheaply. I don't think you can append to strings cheaply, and I'm not sure if you can append to lists cheaply. Probably, I think you can. But anyway, I would just have a loop that returns a vector, and also it's like keeping track of x and y as it goes, but and sort of modifying the map as it goes as well. But it's sort of easier to just read the map once and then enumerate over the map. Since we have to have the map all in memory anyway, it's fine. I'm taking like way longer than I thought I would to describe parse, which is like the easiest function in the world eventually. But okay, so we parse out all the lines from the maze and all the characters from the line. If it's 0, we save that as the special starting position. And if it's any other number, then we add that to the list of pickups. And finally, something that I didn't realize until for a while that I was going to have to do, we have to convert the set of pickups to an immutable set. Because our A* search is going to need to use that tuple, or that set, I should say, as a map key. And ordinary sets are not hashable because they are mutable and therefore cannot be used as hash keys. So I made it an immutable set. Fine. Now we're done with parsing. We've already seen search. So what's the deal with a node? It just keeps track of the maze, which is never going to change, but it's got to have a pointer to it somewhere. Keeps track of the maze that it is traversing, the position that you're currently at, and the list set of pickups remaining to be gotten. Evaluate is pretty simple. We just extract the position and say, well, first of all, if there's nothing left to pick up, then we've won, succeed. Otherwise, if the entry at maze yx is a wall, then we fail. And also, I put this in a try so that if accessing that index doesn't succeed, it'll throw an exception and we'll wind out here and we'll call that a fail as well. Otherwise, if none of that happened, return progress. So I actually had a fair bit of trouble with this method also, because it was just always returning fail no matter what, and I couldn't figure out why. And it turned out that it was because I had written like this, and it just like, I cannot get my head around Python's extremely late scope checks. So like, this actually like in my brain like just shouldn't compile. But that's not true for Python, and so instead it throws an error at runtime, and that got caught by this except. So like, there's a lot of ways I could have fixed that, right? I could have written like except index error or something, which is the only class of exception I actually want to catch. Except I didn't know what index error is called because I haven't written enough Python, so I just said, oh, catch anything. So that's my fault, but that was a problem that I had. Next is the most complicated thing left. We'll get to it in a minute. Actually, yeah, there's nothing else left really. Let's just do nexts. So we extract the position into an xy tuple, or a yx tuple, I should say. We choose a dy and a dx, each -1, 0, or 1, and then assert that we have we have chosen a valid pair, i.e. a north, south, east, or west move. Now we could also do something like for new pos in list of y plus 1x, y minus 1x, y x plus 1, y x minus 1. But you can see like how easy it is to make a mistake typing all that in. I don't think I did. I think I got it right. But it's doing a job that computers are way better at, which is enumerating a list of possibilities in a regular way. Humans are not good at that. We're good at, like, I don't know, making cookies. Who knows? Stuff that computers are not good at. Computers can probably make cookies. They got factories and so on. At any rate, it's pretty simple and very easy to notice an error in this version. There's only 3 things to look at, and we'll just iterate over them, and like the check to see whether we found the right thing is easy. So that's how I do it. I think in Clojure I tend to do it differently, and I'm trying to remember how. I think what I do is I iterate over like a list of lists, and I put well, it's easier for neighbors when you haven't when you want the 8 adjacent rather than the 4 adjacent. I don't know. Anyway, so then we compute the new pos by adding y and dy and adding x and dx. And we check, is it in the pickups list? If so, we have to make a new list of pickups, which is like, in Clojure, you could just call disjoin to like remove a thing from a set, but well, get back a version of a set with 1 fewer element in it. And likewise in Haskell, it would be, I don't know. I don't use sets in Haskell that much, but there's a function to get a thing out of the set. Anyway, so we need a new set that has 1 fewer thing in it. So we build this set comprehension that's like an immutable set, a pickup for each pickup in self.pickups if pickup is not equal to new pos. So removing the 1 item that is the thing. And then I convert that to an immutable set. Otherwise, I set the new pickups to just be the old ones. Now, in principle, I could just do this and forget about this whole thing. New pickups equals this, right? I was a little bit worried that like tearing apart the immutable set and building a new one every time would be expensive for no reason, and so I didn't do that. In Clojure, I certainly would have, because it probably would have returned the exact same set object if there was nothing to disjoin. But I don't know. This seems fine. A little bit wordier to get a tiny bit of performance. It's not always clear where to make that trade-off. But anyway, so for each of these dy's and dx's, if it is a legal move, then we yield a 1 cost move to a node with the new position and new pickups. And as for the goal estimate to guide our A* search, we are basically, what I did is I said, like, remember with A* search, it's important never to overestimate the distance. It's fine to underestimate it. And I was trying to think of like, figure out some complicated thing for like, what's the distance to like all of the different things. I was like, that could lead to overestimating. Let's just assume that no matter where we are, the pickup closest to us is the one that we need to get to win, and then we'll do Manhattan distance from there. So I wrote this distance function that takes a tuple and tells you how close the maze's current position is to that tuple. And then I iterate over all of the pickups we have, and I call min. And that's our goal estimate. And that works fine. It doesn't perform super well. It's like 30 seconds or something. Actually, I think it was less. It was like 8 or 10. So, fine. Great. What happens if we set the goal estimate to be 0? I.e., basically that's turning it into a breadth first unguided search. It still performs fine. It's slower, but not, it's slower by like, I don't know, 30% or something maybe. Nothing outrageous. Okay, so that was part 1. Pretty straightforward implementation. I spent some absurd amount of time on parsing, which is not the hard part, really, or shouldn't be. So what about part 2? Of course, if you leave the cleaning robot somewhere weird, someone is bound to notice. So now they say start at 0, go to everywhere else, and then come back to 0. Okay. So let's check out master and see what I did for that. So the main thing is I wasn't storing 0 as a special pickup. I wasn't storing it as a pickup at all. I was just basically using it to initialize the map's initial position. So, well, the first thing that needs to change is the node class. Oh boy, that highlights a lot. Needs to take an origin as here's where you need to go after you've picked up everything else, right? And so it just saves that. Now, of course, the initial node that we construct when we parse the maze, we could just use pos and origin to be the same. But remember, we're constructing new node objects all the time as we do our A* search. So those will tend to differ rather than being the same. Evaluate is almost the same. We just added this and here that says you're only actually done if there are no pickups and you're at the origin. Fine, the rest is still the same. Next, I believe, was completely unchanged, except we had to add the origin in. Goal estimate, yeah, same thing. I just say the goal heuristic, if there are any pickups left, is the old heuristic, and otherwise it's the distance to the origin. I'm sure there was some clever way to unify this, but I didn't see it immediately, so I didn't do it. And we, in fact, do not have to change anything in parse either. We just have to pass the start node to the constructor twice. And this runs, again, in a reasonable amount of time. So, I mean, that's basically it for what I actually did. But I want to talk a little bit about a better way that... Did I forget to show you guys the thing? I forgot to show you guys the thing. Welcome to Advent of Code 2016, where you're always looking at the wrong screen. What did we look at? Init has a new origin. Evaluate has this extra and clause here. If self.pos is origin, then you can't succeed unless you've picked up all the pickups and you're at the origin. Next does nothing interesting. It just passes the origin again. The goal estimate, I could have left it the same. Well, I guess not, because when there are no pickups, min will throw an exception saying there was nothing there. I could have, as I said, unified it somehow, but I didn't see it. And like basically everything is just not much changes. So that was, as I say, the way I actually did it. But I saw on the Reddit when I was done a really cool way to do it that would be much faster than my like silly A* thing. Which is basically to recognize, rather than to just look at the problem and say, oh, it's a search, over this space, and we're just going to make moves and eventually get to the end. You could recognize this at a slightly higher level. So let's go look at one of the example mazes. So what was described on Reddit is, I think, it's definitely a way better idea than what I did, or certainly a lot cleaner and going to run faster too, is to recognize this as a graph. Well, we treated it as a graph where like every position is a node, and it has neighbors north, south, east, and west, or edges, I should say, to north, south, east, and west. But you can actually sort of abstract over the paths between nodes. If you just treat the pickups as nodes, 0, 1, 2, 3, and 4 as the only nodes in the graph. So what you have to do then is for each node, pathfind to each of the other nodes once, which is going to be relatively cheap compared to pathfinding from one node to every other node. Is it? But yeah, because it's finding 5 short paths as opposed to one long path, and because of like the sort of quadratic growth of how many areas you have to explore when you're building a path of length n, Is it quadratic? I don't know. I think it should be exponential, really, but I don't know. Who knows? It's probably just quadratic because of covering the same space. But the point is, if you do these like 5 times 4 small searches at the beginning of the problem, you can say, okay, well, 0 is a node in our graph, and it can reach nodes 1 and 4, each of them with a weight of 2. That's how long it takes to get there. 1 can reach 0 and 2, and one of them has a weight of 2, and the other one has a weight of, like, what is that, 6? Yeah, 6. And then, once you have that, you treat it as like the traveling salesman problem, or as some other. You could use A star if you wanted. Well, maybe not, because A star is about reaching a destination node. And if you're treating the graph as being these 5 pickups, there isn't really any one of those pickups that is the goal. The goal, rather, is to touch all of them. And so you can model that as A star, where like each node is like not a node on this graph, but a node in some other abstract graph that has what node you're on and which pickups you have. So like you could do that and then run an A star search on that graph, and you could do it. But it turns out there's only like 8 or 9 pickups, which, like, how many permutations are there of 8 or 9? Like, not that many. A few thousand, maybe. A few 100,000, maybe. And so you can just, for each of them, compute the expense of just add together all the weights, and like it's very fast. Much faster than searching this very large search space with A star, to recognize this as an instance of a more abstract problem. And then when you add 0 back into the pickups list, it's like finding a Hamiltonian circuit, and like, I don't know, apparently there's some well-known algorithm that is slightly faster than the obvious one, but permutations is still plenty good. And indeed, A star search is plenty good, but it's a bit clumsy to, a brute force hammer that we solved once in day 11 and we've been using over and over through advent of code. So I don't know, it would have been nice to do this in a more interesting way, but I didn't. I did it this way. So there you go. Okay, so that was day 24. We're not going to do day 25 in this episode, but should be up in the next episode. And it's going to be the last one. I'm going to miss this series. But let's not say our goodbyes just yet. We'll save that for tomorrow. Anyway, thanks for watching, and I'll see you next time.